The rule of thumb in setting ground fault protection for circuit breakers generally involves a percentage of the calculated symmetrical fault current. A common recommendation is to set the ground fault protection at approximately 5 to 10% of the symmetrical fault current that has been determined for the specific circuit. However, it's important to understand that this 5 to 10% figure is a rule of thumb and should not be considered a universally applicable value. The actual setting needs to be carefully chosen based on the specifics of the application, the characteristics of the equipment being protected, and the overall system design. There are situations where a setting outside this 5 to 10% range may be necessary to achieve optimal protection and minimize unwanted tripping. Let's delve deeper into why this rule of thumb exists and what factors influence the final ground fault protection setting. The symmetrical fault current represents the theoretical maximum current that could flow during a three-phase fault condition in a balanced system. Ground fault currents, on the other hand, are typically lower in magnitude than symmetrical fault currents. They occur when an unintended path to ground develops, such as when insulation fails and a live conductor comes into contact with a grounded surface. Ground fault protection is designed to detect these ground fault currents and quickly trip the circuit breaker to prevent damage to equipment, reduce the risk of electrical shock, and minimize the potential for fire. The 5 to 10% rule of thumb is based on the idea that ground fault current should be significantly lower than symmetrical fault currents. By setting the ground fault protection pickup level at a relatively low percentage of the symmetrical fault current, the system can be made sensitive to ground faults while still providing adequate protection against high-magnitude fault currents. The goal is to strike a balance between sensitivity and selectivity. Sensitivity refers to the ability of the ground fault protection system to detect even small ground fault currents. Selectivity, also known as coordination, refers to the ability of the system to trip only the circuit breaker closest to the fault, minimizing disruption to the rest of the electrical system. However, there are several factors that can influence the optimal ground fault protection setting, making it necessary to deviate from the 5 to 10% rule of thumb. Firstly, the type of load being served by the circuit is an important consideration. Circuits that serve sensitive electronic equipment, such as in data centers or hospitals, may require more sensitive ground fault protection settings to prevent even small ground fault currents from causing damage or disruption. In these cases, the ground fault protection may need to be set at a value higher than 10% of the symmetrical fault current to ensure adequate protection. Conversely, circuits that serve less sensitive loads, such as lighting or general-purpose receptacles in a residential setting, may be able to tolerate lower ground fault protection settings without compromising safety or equipment protection. In these cases, the ground fault protection may be set at a value below 5% of the symmetrical fault current to reduce the risk of nuisance tripping. Secondly, the length of the circuit conductors can also affect the optimal ground fault protection setting. Longer conductors have higher impedance, which can limit the magnitude of ground fault currents. In these cases, it may be necessary to set the ground fault protection at a low value to ensure that the circuit breaker will trip quickly enough to prevent damage to equipment. Thirdly, the available fault current at the point of application is a critical factor. The symmetrical fault current calculation provides an estimate of the maximum available fault current, but the actual fault current may be low due to factors such as source impedance, transformer impedance, and conductor impedance. It's essential to perform a thorough short circuit study to determine the actual available fault current at the point where the ground fault protection is being applied. This study should take into account all relevant factors, including the utility source impedance, transformer impedance, conductor lengths and sizes, and the impedance of any other equipment in the circuit. The ground fault protection setting should be based on the actual available fault current, not just the calculated symmetrical fault current. Fourthly, the coordination with other protected devices in the electrical system is also important. Ground fault protection should be coordinated with other overcurrent protective devices, such as fuses and circuit breakers, to ensure that the device closest to the fault will trip first, minimizing disruption to the rest of the system. Coordination studies are typically performed to determine the optimal settings for all protective devices in the system, taking into account their time current characteristics and the available fault current at each location. Fifthly, the National Electrical Code, or NEC, provides guidance on ground fault protection requirements for various types of electrical systems. The NEC specifies when ground fault protection is required and sets limits on the maximum ground fault protection settings. It's essential to comply with all applicable NEC requirements when setting ground fault protection. For example, NEC Section 230.95 requires ground fault protection of equipment for solidly grounded wire electrical services of more than 150 volts to ground, but not exceeding 1000 volts phase to phase for each service disconnect rated 1000 amps or more. This requirement is intended to reduce the likelihood of destructive arcing ground faults on large electrical services. The maximum ground fault protection setting is 1200 amps. It is important to note that the NEC requirements are minimum requirements, and it may be necessary to provide more sensitive ground fault protection in some cases to adequately protect equipment and personnel. Sixthly, the specific characteristics of the ground fault protection device itself can also influence the optimal setting. Different ground fault relays and circuit breakers have different operating characteristics, such as pickup current, time delay, and reset time. These characteristics should be considered when setting the ground fault protection to ensure that it will operate correctly and provide adequate protection. Some ground fault relays offer adjustable settings for pickup current and time delay, allowing for greater flexibility in coordinating the ground fault protection with other protective devices. Seventh, it's important to consider the potential for nuisance tripping when setting ground fault protection. Nuisance tripping occurs when the ground fault protection trips unnecessarily, disrupting power to the circuit and causing inconvenience or even equipment damage. Nuisance tripping can be caused by factors such as transient voltage surges, harmonic currents, or ground loops. To minimize the risk of nuisance tripping, it may be necessary to set the ground fault protection at a slightly higher value or to use a ground fault relay with a time delay feature. Eighth, regular testing and maintenance of the ground fault protection system are essential to ensure that it will operate correctly when needed. Ground fault relays and circuit breakers should be tested periodically to verify their calibration and operating characteristics. The testing should be performed by qualified personnel using appropriate test equipment. Any necessary repairs or replacements should be made promptly to maintain the integrity of the ground fault protection system. Ninth, documentation of the ground fault protection settings and testing results is also important. The documentation should include the calculated symmetrical fault current, the actual available fault current, the ground fault protection pickup setting, the time delay setting, and the date of the last test. This documentation will be helpful for future troubleshooting and maintenance. In summary, while the 5 to 10% rule of thumb can be a useful starting point, the actual ground fault protection setting should be based on a thorough engineering analysis that considers all relevant factors, including the type of load, the length of the circuit conductors, the available fault current, the coordination with other protective devices, the NEC requirements, and the characteristics of the ground fault protection device itself. It's also important to minimize the risk of nuisance tripping and to perform regular testing and maintenance of the ground fault protection system. Remember that setting ground fault protection requires expertise and should be performed by a qualified electrician or electrical engineer. Incorrect settings can lead to either inadequate protection or nuisance tripping, both of which can have serious consequences. The process often involves a detailed short-circuit study, coordination analysis, and a thorough understanding of the electrical system being protected. The goal is to select settings that provide reliable protection against ground faults while minimizing the risk of unwanted outages. So, while the 5 to 10% rule of thumb provides a general guideline, the final decision on ground fault protection settings should always be based on a comprehensive engineering evaluation and a thorough understanding of the specific application. In complex electrical systems, it is recommended to use advanced simulation software to model the system and analyze the impact of different ground fault protection settings. These simulations can help to identify potential coordination issues and optimize the settings for maximum protection and reliability. It is also important to consider the impact of ground fault protection on the overall system grounding scheme. The grounding scheme should be designed to provide a low impedance path for ground fault currents to flow back to the source, ensuring that the ground fault protection will operate quickly and effectively. There are several different types of grounding schemes, such as solidly grounded, impedance grounded, and ungrounded systems. Each type of grounding scheme has its own advantages and disadvantages, and the choice of grounding scheme should be based on the specific requirements of the application. Solidly grounded systems provide the lowest impedance path for ground fault currents, but they can also result in high fault currents that can damage equipment. Impedance grounded systems use a resistor or reactor to limit the magnitude of ground fault currents, reducing the risk of equipment damage. Ungrounded systems do not provide a direct path for ground fault currents, but they can be more susceptible to transient overvoltages. The selection of the appropriate grounding scheme should be coordinated with the ground fault protection designed to ensure that the system will operate safely and reliably.